This talk is a summary of the hit and run model that was published in the memoir 2020 from the Geological Society of America. The authors are Tikoff, Housen, Maxon, Nelson, Trevino, and Shipley. The short version of the model can be given by these two cartoons. There are terranes in the Canadian Cordillera now that used to be located significantly further south. They are the one closer to the North American margin called the intermontane, and the one further from the margin called the insular. The idea is that the insular terrane collides at about 100 million years and goes up the coast but slowly in sort of an oblique collision, and then it moves from about at 85 million years to moving up very quickly up the North American margin. We're sure it's located next to North America because the insular terrane gets sediments that could only be from North America during this time. But let's talk about how we got to this model. The Canadian Cordillera is full of terrain. So we just talked about the insular terrane, which is the one shown in pinks and purples. I've left out the peninsular terrane, and that was left out in the model as well, although likely that was also going along for the ride. Inboard of that, I'm going to introduce another one called the intermontane terrane, which is the one in greens. So the overall argument is that the insular terrane collides with North America at some latitude at 100 million years. And we know that because of deformation that's occurring on the eastern margin of the insular terrane. We have good paleomagnetic data from much of the Canadian Cordillera, and the insular terrane in particular looks to be 3,000 kilometers south of its current location at that time. So we first have to talk about how that's determined, so the paleomagnetic data. And Bernie Housen was the person who summarized this data in the Tikoff et al. Paper. If you look at North America, what's shown in the black dots are all the places on the Cordilleran terranes, the exotic terranes, that have paleomagnetic data. And each of those corresponds to a paleomagnetic pole shown either in yellow, for those are for the insular terrane, so that's the outboard terrane, or in blue for the intermontane, which is the more inboard terrane. And what you can see is the poles of those sites do not correspond to the poles of North America, which are shown in the circles or the ellipses of orange. So if you look at the further south one, North America at 130 to 85 million years, the pole of North Pole was sitting basically at the north end of Alaska. At about 80 million years to 60 million years, it was located further north, which means North America had to move south sometime during this interval. It's probably easier to think about it, though, in terms of this. Now I've color-coded the insular terrane as yellow for paleomagnetic derived sites, or one site that actually contains information about paleolatitude from fossils. The North Pole, again, nearly at Alaska during this time, and you can see that all the data from approximately 100 million years, which is what's shown on the left, is significantly further south than their current locations. If you check back in at about 85 or 80 million years, you'll see that everything is moving north, but it's still not yet in its current positions. And so what we've captured with the paleomagnetic data is not just the fact that it's further south, but with the fact that it's moving north, and at the same time, North America is moving south. If we plot this now in age on the x-axis and displacement with respect to North America, and that's using the pole that Bernie was using, which is the one that's based on North American only data. If you look at just the yellows, what you can see is there's this clear trend of northward moving starting at about 90, and every time you step forward in time, it seems like the insular terrane is moving north. The data is very consistent with each other, and it's recording northward motion. The intermontane terrane, again, the stuff that's further east or more inboard, also shows northward motion, but not as much. So that was where we started with the 2023 paper. We summarized the paleomagnetic data, and that was mostly the work of Bernihausen. We assumed it was correct then, and we are now looking at the geologic consequences. So what's shown on the right-hand side is the hit, which is the insular terrane, and where it would be located at approximately 100 to 85 million years. Notice that I have not put it adjacent to North America, but just showing its paleolatitude, and the intermontane terrane, and that it's also located further to the south. And then, through time, it has moved north. And so the idea is that in fact, the insular terrane hits at the latitudes of between Baja California and about Idaho, and then it moves north, which is what the paleomagnetic data is saying. Why the paper is interesting is because it gives up on three models. It says that there wasn't continuous Farallon subduction, which is often assumed. It also says that shallow slabs might not be why we have the features we have, such as the block uplifts, or, for instance, that's why the coastal batholiths shut off. And then the last point, and it's sort of a bigger point, is that orogenic belts can be explained by two-dimensional models, that any cross-section, what the hit and run model is saying is that basically most cross-sections are going to be wrong because they basically only show part of what's going on. All right, if we wanted to look at the plate geometry right before the insular terrane collision, we would look something like this. Geologically, you can't tell the difference of the two different columns, but Spencer Fuston, working with Johnny Wu, suggested that the one on the left is more likely correct based on their models of slab subduction. So we're going to roll with that one for the time being. So if you look at just North America, which is the right-hand side, and I'll take the Sierra Nevada, is that there's an arc at about 110 million years that's subduction related. But the insular terrane is also coming in on that subducting plate, and it is going to attach to North America at about 100 million years. And moreover, the collision itself is not going to be a head-on collision, but it's going to be one that involves dextral or right lateral motion up the coast. This somewhat busy diagram is trying to show four different steps. 110, which is pre-collision, and so you have the insular terrane off-board, this other, what looks like a thrust fault, which is a subduction zone offshore North America, and it's offshore from, and then I should say, on the right-hand side shows where you are on the margin from Mexico, Baja, Mojave, sort of Central California, Idaho, British Columbia, and so forth. And so prior to that, you've got two subduction zones going, but you shut off the one under North America as the insular terrane collides, and that basically is the hit. That continues till about 85, where the slip on the fault stops being further back in the magmatic arc and pushes towards the plate margin, and then it starts moving up the coast relatively quickly to get in place by about 55 MA. So the hit between 100 and 85, when it's not moving up the coast very much, is the first stage, and then the second run stage is when it's moving up the coast quite quickly, but it's still acting on the western edge of North America and causing shortening. This is a relatively busy picture that talks about the different features you see. I'm going to go through them in order, but I'm going to concentrate on the magmatic arc, the hinterland, and then the severe fold and thrust belt. But for instance, there's good evidence that the block uplifts in the western United States are coming up not just after 85 million years, but they're actually starting at about 100 million years. The Idaho part of the margin turns out to be a critical part, and the argument from the 2023 paper basically was looking for how points of agreement. And on the left is a very important paper. It was written by Sandra Wild and colleagues, and what they did is restored faults in the Canadian Cordillera, mostly right lateral, and what they noticed is the insular superterrane, which is what sits on the far left side, restores to northernmost California. And that's simply restoration based on existing faults, and this is their 100 million years. So they're suggesting that the insular terrane must have hit at 100 million years and North America. let me be more clear. They say it's restored to this point. My argument and our argument in the paper is it's actually hitting at this time. And that's everywhere in from the Idaho margin and the western Idaho shear zone. The alternative mobilist option is just to say that the Paleomag corrects, but even in this case, the northern end of the insular super terrane, and this isn't counting adding the peninsular terrane on, is also located in Idaho. So the idea is, either way, Idaho records a terrane collision. So we would say, okay, let's look in Idaho to see what goes on. And Idaho has undergoing significant deformation. It starts at approximately 100 million years, and it's transpressional, which means it not only has right lateral motion, so there's a dextral component, but it also has a shortening motion, and that shortening motion gives you vertical lineations and flattening strains, but it's still rotating things around a vertical axis. So that's the northernmost arrow, and again, it's directly inboard by anybody's interpretation of the insular super terrane hit. The point about this, and this is new data that although we knew about it, wasn't published at the time, was if you look at the Sierra Nevada batholith in California, significantly further south of Idaho, and you looked right in the central Sierra, you get a series of shear zones. We've known the ones that are on the east margin for quite some time at this point. They go to about 85 or 80 million years. They started 92 million years, but it turns out that there's a whole series of shear zones that seem to start at about 100 million years. And they look exactly like what we see in the western Idaho shear zone. So as I show you this picture, both Idaho and California have a mid-Cretaceous intra-arc shear zones. They turn nice granites into orthogneisses with east-dipping foliation, down-dip lineations, and flattening strains. And one of those photos is from Idaho, and the other is from California, at exactly the same time, in exactly the same rock type with exactly the same kinematics. So the one on the left is California, the one on the right is Idaho. The point being, there's something going on in the magmatic arcs at this time. And it's not a surprise that they are. So B is the current interpretation from Kistler 1990 that says there's a whole series of offsets within the arc that are tracked by the strontium 706 line, and that the offsets correspond to these interbatholithic breaks, which are right lateral shear zones. If you restore those shear zones, what it shows is that there's an old Precambrian transform located that basically went right through the Sierra Nevada, and then that whole system starts moving to the north in the late Cretaceous through Paleogene. Since this data, since the hit and run model was published, there's now new information from the Sierra Nevada. So what you can see is a map on the left and cross sections on the right from Green et al., where they show intense folding of the rocks and lots of sort of cryptic strike slip faults. And they know the age of the youngest units that are folded, which are 105, and they know the age of the granitic rocks that intrude, which are 98 million years. And so this deformation event is very strong and constrained to be at approximately 100 million years. Again, consistent with a hit and run model, and Green et al. Also point that out. If you look inboard or eastward from the Sierra Nevada and Idaho arcs, what happens is you start to pick up crustal-derived magmatism. So this is not arc-derived or subduction-derived magmatism, but rather magmatism associated with melting of the crust, which is caused by thickening of that crust. And it takes about 10 million years to thicken the crust enough to start making it melt. So again, that's consistent with a crustal thickening starting at somewhere 100 to 95 million years. The last thing that's very consistent with that is the severe fold and thrust belt. There is an earlier history that's nowhere near as intense that starts about 125. There seems to be a hiatus at about 105, and then at 100, the fold and thrust belt becomes very active. And that's very well documented because of the foreland sediments, among other things. So the idea is, once again, the whole origin seems to be responding very quickly to this 100 million year event. There's also evidence, again, of foreland uplifts starting at this time. So these foreland not all of them, but some of these foreland uplifts are starting. Now we're going to go to the second phase, which is called the run. And here, the insular superterrane is not covering Mojave or Baja sections of the arc because it is moved further north at this point, and it will continue to move north. And again, this is showing the different features you'd see at the different sort of west to east parts. Sort of schematically, what's happening at this point is basically the insular terrane is moving north, but the intermontane terrane is all superterrane. It's also moving north at this time. That's constrained by some paleomagnetic data from the Carmax group, which requires that the intermontane terrane is moving. And since the insular is outboard, it also moves with the intermontane, even if there's no strike slip between them. Little pieces of the intermontane get left behind, such as the Blue Mountains in eastern Oregon. So we get dextral strike slip faulting up the coast. It's cryptic, but we see it. We get cessation of magmatic arcs in this model because the insular terrane is simply blocking them. And then we get continued deformation and uplift in the Rocky Mountains, including in these block uplifts. So these are the Rocky Mountains of Colorado and Wyoming. So to provide a little context here, the prevailing model for what goes on in the Cretaceous through Paleogene in the western United States is called the shallow slab model. And it was a good model to try and explain how you had normal subduction up to some point, after which you get the subduction zone shallows and you shut off the continental magmatic arcs, and then you get diffuse uplift in these block uplifts. So for the data that existed in the 1970s, it was a reasonable model. It's very two-dimensional. The model, however, is not compatible with transpirational deformation in the magmatic arcs. This doesn't make any sense. There's no three-dimensional aspect of it, nor is there any indication that it starts at 100 million years. It's also not compatible with the seismic tomography, and the reason for that is we don't see a shallow slab at all. What we see are dipping slabs in the mantle, and we see a distinct change at about 100 million years, according to the Fuston et al. Papers. And the third thing is it was never compatible with the paleomagnetic data, which pre-existed the articulation of this model. The alternative then is this 100 million year event. And what's becoming clear is this 100 million event is obvious. It's everywhere. It's kind of surprising that we didn't see it, and I think we couldn't see it because it didn't conform to our models. The paleomagnetic data, however, provides a very simple answer to that question. Of the reason we have uplift everywhere is we have an oblique collision at exactly that time, and that the Laramide block uplifts are a result of this collision. So, and this is the first articulation of the hit and run by Maxon and Tikoff 96, where the Baja BC, or the insular superterrane, basically stops coastal magmatism, creates a magmatic gap, causes a orogenic plateau, thrust faults, and a block uplift. And I'm going to make an important point, and the Tikoff et al. 2023 paper also is making the similar point, which is, this is from Thomas Kuhn, who wrote The Structure of Scientific Revolutions. And he said the decision to reject one paradigm is always simultaneously the decision to accept another, and that the judgment leading to that decision involves comparison of both paradigms with nature and with each other. So what he's saying is scientists won't basically say something's wrong, but we don't know what's right. They basically sort of require a different model to look at it. So the hit and run model is useful in this way. That basically it's another way to explain the data, and it does a much better job of explaining some of the data. Another big debate, if you're a mobilist though, is where is the slip? So Bob Hildebrand suggested the slip could be further east, so within the thrust fault system, and then somehow linking up to the Rocky Mountain Trench in Canada. I suspect that's not the case, and the hit and run also suggests that it's moving along the California margin. And I want to be clear here, that's the insular superterrane. There's no question that the intermontane superterrane is moving north, and it's moving north, has to be moving on the northern Rocky Mountain Trench as well. A nice study by Erica Boudreau et al. In 2025 adds another piece of paleomagnetic data, the Gold Beach terrane, which is here. What's interesting about the Gold Beach terrane, it's a little bit that got left behind. It's currently located offshore Oregon, but if you look at its paleomagnetic signature, it must have started in southernmost California. So here it is on the right-hand side, starting in Southern California, and it has the tidal signatures that are consistent with starting in that orientation. And what's shown in blue now is the insular superterrane. And what's interesting about the Gold Beach is it's getting some detritus, it looks like, from the insular superterrane as well as from North America. So it's getting both sides, and the Paleomag has it in Southern California. So this is yet sort of new information since this came out. It also suggests, and this is the important part, that there has to be major slip up the California margin to get this into place. So the conclusions overall are that the deformation we see as severe and laramide orogenies are really a result of oblique collision and subsequent northward motion of the insular superterrane with North America. The evidence is the paleomagnetic data, but also that the insular superterrane has deformation at 100 million years, which isn't really talked about in the Tikoff et al. Paper. That's data from Rubin, Russmore, Cowan, other people who've been working in that region. There's also evidence from mantle slabs that there was a rearrangement in about 100 million years. And the things that's focused on in the Tikoff et al. Paper are, in addition to the paleomag, are that the magmatic arcs all go to dextral transpression at 100, that the severe and laramide deformation starts in earnest at this time, and that there's the magmatic arc cessation and then the hinterland timing are both consistent with sort of shutting off of subduction at 100 and then thickening by about 85.